So in subtopic 1.3, we've been looking at uniform circular motion, and now we're going to look at gravitational forces, and eventually we're going to look at satellites and their applications. So, in this first part of the video, you need to know that objects with mass produce a gravitational field in the space that surrounds them. You need to know that an object with mass experiences a gravitational force when it is within that gravitational field of another mass. You need to know that gravitational field strength can be defined as the net force per unit mass at a particular point in the field, and that's expressed quantitatively as G. So G, the gravitational field strength, is equal to the net force per unit of mass, so F over m. And that's actually just equal to the acceleration due to gravity, because acceleration is F over m, and the magnitude of the acceleration due to gravity at the surface of the Earth is 9.8 meters per second squared, which we're well aware of. So, as stated above, an object with mass produces a gravitational field in the space that surrounds them. So we have the Earth here in the top right hand corner. We have a gravitational field in the space around the Earth, and the strength of that field decreases with distance r from the center of that object or that mass. So as we can see, these gravitational field lines, these gravitational field acts towards the center of the mass, and the gravitational field is a vector quantity, so it's defined by these arrows. So these arrows are pointing towards the center of the mass, or Earth, and you'll notice that the spacing represents the strength. So at the surface of Earth, these gravitational field lines are much closer together, and then as we go further and further away from Earth, we have more and more space, so the gravitational field strength is weaker. So the surface of Earth gravitational field strength is approximately 9.8 meters per second squared, and as you go further and further away, gravitational field strength is weaker and weaker. And any mass that is within any object that has mass, when they're placed within this gravitational field, they're going to experience a gravitational force, a mutually attractive force, which we'll discuss later. Now, the gravitational field strength is defined as the following. You are expected to know this, but it's very rare that it would come up as an exam question. So the gravitational field strength G at a point is the net force experienced per unit of mass on a particle when placed in that point in the field. And quantitatively, it's this. So G is the field strength, gravitational field strength, is equal to the force experienced per unit of mass at a point in the gravitational field. So this formula is on your formula sheet, and it's easy to remember the definition from this. So gravitational field strength is equal to the net force experienced per unit of mass at a point in the gravitational field. Now, as we know from Newton's second law of motion, force is equal to mass times acceleration. So obviously, rearranging this, we know that acceleration is equal to a force per mass. So the gravitational field strength is equivalent to the acceleration due to gravity experienced on a planet. So these two things are equivalent to one another. Gravitational field strength is equivalent to acceleration due to gravity. So, for example, a 100 kilo mass experiences a gravitational force of 980 newtons on the surface of Earth. Calculate the gravitational field strength. So the gravitational field strength would simply be the force experienced per unit mass. So it's going to be the 980 newtons divided by the 100 kilo mass, which is 9.80 meters per second squared, or newtons per kilogram. Now, additionally, as we've said, all objects with mass attract one another with gravitational force. And as we've said previously, Objects that have mass have a gravitational field within them, and any object with mass actually experiences a gravitational force within that gravitational field. Now, Newton also came up with a law of gravitation, law of universal gravitation, that governs the magnitude of the force, the gravitational force. So, all objects with mass attract one another with a gravitational force, and the magnitude of this force can be calculated using Newton's law of universal gravitation, which is this one down here. So, every particle in the universe attracts every other particle with a force that is, if we look down here, that force is directly proportional to the product of the two masses, and it's inversely proportional to the distance between them squared. So the distance between the center of the masses, technically. And it's also the force, so experimentally this was derived, and there was some sort of constant, and this here is the gravitational constant, which is, if you look on the next page, this gravitational constant is 6.67 times 10 to the minus 11, and then the units don't matter, but this is on your formula sheet, this constant, so you don't need to memorize it. So, as stated on the previous slide, any two particles with mass experience a mutually attractive gravitational force between the center of the masses. So, the forces are equal in magnitude, but opposite in direction, because as we know from Newton's third law of motion, every action force has an equal and opposite reaction force, and this holds true for gravitational forces. So the forces are equal in magnitude, the gravitational forces are equal in magnitude, but opposite in direction. And now, as I explained previously, the gravitational force between those two masses is directly proportional to the product of the two masses, so M1 and M2, and it's inversely proportional to the distance between the center of the masses squared. So the further apart the masses are, the magnitude of the force between them is going to drop off significantly, because it's times by 1 over r squared, where r is in meters and masses are in kilograms. Everything is in standard units like usual. And as I stated previously, this is known as Newton's law of universal gravitation, and this is on your formula sheet. So masses in kilos, distance between them in meters. And it's super vital that you understand that the forces act in pairs, and they're equal in magnitude and opposite in direction. So, you need to be able to solve problems using Newton's universal law of gravitation. It's quite a simple formula to use. So, determine the gravitational force acting between two astronauts A and B, separated by a distance of 50 meters, if their masses are 105 and 110 kilos respectively. So the gravitational force between them will be the universal gravitational constant times by the product of the masses of the astronauts over the distance between them squared. So it's going to be 6.67 times 10 to the minus 11 multiplied by the masses, 105 times 110, divided by the distance between them in meters squared. And you type that into your calculator. You'll get, how many significant figures do we have? 3. So 3.08 times 10 to the minus 10 newtons. And that's going to be, just going to pause it for a second.